So basically here, I want to do a little bit of more synthetic division. And this is something we did last time, the division algorithm. So I did point this out last time. If you remember, which I hope you do, that what the division algorithm is saying is, just like we can divide integers, when you divide one integer by another, right, you get a quotient and a remainder. You can do the same thing with polynomials, in fact. Namely, if you have a polynomial, capital F of x, and if you're dividing it by a non-zero polynomial, d of x, you'll get two unique polynomials, q and r, so that capital F, right, the dividend as we call it, divided by capital D, the divisor is going to equal to q, the quotient, plus r of x over d of x. R of x is the remainder. Not only that, okay, from here, if you were to multiply both sides of this equation by capital D, you can write it this way. Both of them turn out to be, both equations here turn out to be very useful. I mean, as far as I know, we're going to use this one more than this one, but we will use this one today. But anyway, you get the division algorithm for polynomials. This capital R of x, the remainder, it's either identically 0, so it's 0, the 0 polynomial that is, or its degree is less than the degree of d. One or the other. And with synthetic division, what we do is we're going to focus on when d of x looks like this. That's what happens in synthetic division. And what's nice about that is, if you apply the division algorithm in that case, you can actually obtain two nice results that I did present last time. The remainder theorem, which basically tells you what the remainder is. It actually, if you divide by this, the remainder turns out to be capital F of A. And in fact, from there, or you can get R of x is 0. And in fact, from there, you get the factor theorem, which tells you that d of x, this thing, is a factor of f exactly when f of that a is 0. It's just stuff I did last time, so I don't want to go through it all again too much. I did present the factor theorem here as well, again, I guess just as a reminder. I know here I have a lowercase f, but most of the things we've been dividing by, I called lowercase f. But again, this is just saying that this has x minus a as a factor, if and only if f maps a to 0. That's what I was trying to say. It's mostly because if you divide this by x minus a, by synthetic division, you get this as the remainder. And this is a factor of this if and only if the remainder is 0. That is, if this is 0. If and only if this is 0. Okay. And again, that's just stuff I did last. Just quickly get rid of that. Basically here, so I just wanted to delete that. I'll write it out again. But here, we're just doing an example where we have x cubed minus x squared minus 14 times x plus 4, right? And we're going to divide it by x minus 3. First, we can actually determine the remainder, even without dividing, right? We can use that factor theorem. Namely, is x minus 3 a factor of this? Well, let's see what f of 3 is, right? By the factor theorem, this is a factor of f if and only if f of a is 0. A in this case is 3, and f is this. So this is if and only if f of 3 happens to be 0. So if I plug in 3 in for x, I get 0. So right away we know that x minus 3 is a factor of this. In other words, if we divide this by x minus 3, we are going to get a remainder of 0. What's the quotient? That's a different story. That we have to figure out. For the quotient, you actually have to divide, and that's what we're going to do, although we're going to use synthetic division. In particular, we're going to get the other facts. Okay, so what happens? Again, this is x minus 3. So the 3 I bring over here. Right? If this was x plus 3, as we saw last time, if it was plus, you have to replace this by minus a negative, and you would have negative 3 here. It's x minus 3, so the 3 stays here. From here, right, what happens is the coefficients you're going to list. It has to be in standard form, right? Remember, that means as you read it from left to right, the powers of x have to decrease. Any missing powers, you put in 0 as a placeholder. Okay, well, that's what we're doing. So the 1, this comes straight down. And then remember, what do you do next? You have 3 times 1. That's equal to 3. That product goes here. Then you're going to add these two to get this. So again, follow what I just drew, so to say. 3 times 1. Okay. That's equal to 3. That product goes here. The sum, you get the sum. That sum goes here. Then you repeat. In other words, you have 3 now times 2. That's going to go here. And then you add. You get negative 8. That's what happens there. Then you add. You get negative 8. 3 times minus 8. That's minus 24. 24 and minus 24 is 0. Remember also, to actually get the quotient here, it's always 1 degree, since we're doing synthetic division, it's 1 degree less than the dividend, which is here, the original polynomial, f. So these are the coefficients of it. So we have x squared, 2x, minus 8. The last column, this number here, is the remainder. So our remainder is 0, which we expected because of what we have here. So we have this. That's our first example of synthetic division. Again, normally let me write out actually what I had there. Normally what happens is, in this case, you would have f of x, from the division algorithm, right? You would have a d of x times a q of x plus, normally you would have plus the remainder. Although in this case, again, our remainder is 0. 0. That's what happens. All right, so we have this example done. And notice also, we can actually keep on going if we wanted to. Namely, as I have over here, we divided and got this here. So that is, we have x minus 3 as a factor, but we can actually factor this. Namely, for this one, if you went back to the way we factored trinomials, of degree 2, leading coefficient 1, right? Remember what you do? You want two numbers whose product is, in this case, negative 8, the constant term. The sum of those two numbers has to be the coefficient here, which is 2. I know the answer is here already, but we want two numbers whose product is minus 8 and whose sum is 2. So, of course, 4 and negative 2 pull that off. And so that tells us we get x plus 4 times x minus 2. Plug it in here, we get the factorization. So we can use division to get the factorization. So that's good. I mean, factoring polynomials, is not easy to do. I mean, although for this one, we probably could have done factor by grouping. There's 4 terms here. But what's nice is we don't have to. So, okay, that's good. So that's our first example today. Now what we're going to do is we're going to kick this up a notch. Actually, before I get to that, let me just say this. Kick it up a notch, what I mean is synthetic division, we did x minus something. What if this leading coefficient is not 1? What if instead we had a number here? So let's say we had a times x minus b. Can you use synthetic division on that? Well, you have to do some work first. That's what I'm going to show you here. So we want to divide this by this here. Now we want to see if this is a factor, right? It looks like we cannot use synthetic division, right? Because the leading coefficient's not 1. What we can do, however, is this. Basically, we want to calculate this quotient. Divide a polynomial by this. And to see if it's a factor, we want to know what the remainder is. Now, it does look kind of nasty. I mean, I guess theoretically, you could dive in and do polynomial long division itself. But let's not do that.